Hello again, it's Jolly. All right, this one is going to be talking about alkenes and oxidative cleavage. I'm going to do alkynes and oxidative cleavage in a different mini video just because there's so much information on the alkenes to start with. All right, I'm going to go to the notes. Where are you? So we are going to talk about these three. Actually, no, one, two, three. Oh, yeah. So we're going to talk about the epoxidation, we're going to talk about dihydroxylation, and then we're going to talk about ozonolysis. Okay, now those are specifically named reactions, and then oxidative cleavage actually breaks bonds. So those are the ones that we're going to talk about in this video. But before we do that, I think a nice little explanation of oxidation might be in order here. Now, I know we've learned about oxidation and reduction in Gen Chem. I am talking about the exact same thing, but in organic chemistry, we of course simplify it because we like to simplify everything. All right, so oxidation is exactly like you learned in Gen Chem. It is the loss of electrons. True. But in organic chemistry, it's generically called gaining of oxygen, or if you will, a polar bond. Reduction, on the other hand, is the gaining of electrons. But for us, we're going to start saying we are gaining hydrogens or losing polar bonds. Okay, so just generically. And let's just start with an alkane. So for instance, if I had an alkane, the generic symbol for oxidation is that. The first thing I would do is put on a single bonded oxygen or an OH. Then, if I continued to oxidize, okay, so the first one is a single OH. The second step would be to double bond that up. And the third would be, if you can, okay, you have to have a hydrogen to give. In this case, I drew it as there was. Okay, so if there is a hydrogen directly connected to that carbonyl, if that is true, then I may add one more single. OH. So that is the steps of oxidation. Now, if you want to obliterate the thing, you can convert this to CO2, but we'll talk about that in a different video. All right, so there are your steps of oxidation. Well, guess what? Reduction is exactly backwards. You would go from a double bond and a single bond, so a carbonyl and a single bond to O, to just a double bond, which would then go down to just your single bond, which would then go down to your alkane. Okay, so that's just generically when I say oxidation and reduction, that's what I am talking about. All right, go back to the notes. Go back to the alkenes. That goes by so fast, it's a little nauseating. All right, so the formation of 1,2-diols or something called a glycol. 1,2-diols just means vicinal. Okay, so a vicinal diol is called a 1,2-diol, or this thing is also called a glycol. Yeah, I know we have so many names for the same things. So how can we actually create this? Well, there's actually a few different ways, and so we're going to do two of them. I'm going to use the reagent potassium permanganate, and then I'm going to show you osmium tetroxide. And every time I show you two, there's usually a power to, both of them, or there's a limit to one of them, so I had to give you a second. All right, so the potassium permanganate, it can over-oxidize. It's very strong. So we have to be very careful, and so we can control it with temperature. So I love it, except it can get a little overzealous. So if we don't want to use that one, we'll use something called osmium tetroxide. All right, let's start with my favorite little alkene. And so we're going to do potassium permanganate. Mn double bondo, double bondo, double bondo. O minus. Okay, so there is potassium permanganate. And do you see these wonderful lone pairs on that oxygen? It is going to come and sit right on top of that alkene. Okay, so it can sit on the top or it can sit on the bottom because the alkenes are flat, and it's going to create this thing. Again, a very generic mechanism. Okay, so it's going to create this. It's not called a square or anything, but the manganese is now attached to the alkene. Well, if you want to get rid of it, you actually have to do a second step. So the first step, looking at my reference, get all the details. So the first one is KMNO4 in water under basic conditions. And I'm going to put the word cold because I want to do this step and not go any further. Okay, so there's your first step. Your second step, I have to get this off. And so I am actually going to use just, a little bit of water or acid. Okay. And it's going to create that. And then MnO2 is the byproduct. This, remember, is syn addition. So those OHs are on the same side. They're on the exact same side. So this is a diol, a 1,2 diol, or we could call it a glycol, but that is one way to put them on. But the key is this potassium permanganate, if we're not careful, can go on and actually cleave through that bond. It can actually cleave through it. Well, what if we don't want to cleave through it? Well, you better control the temperature with cold. Now, if you'll notice, those two are the same thing. So it's all lumped into one, even though I separated this mechanism into two parts. Okay, so if you will, this was one and that was two, but you can lump them all together and end up with the diol in one step. All right, that's potassium permanganate. Well, what if you don't want to use potassium permanganate and out of room? So I'll go over to the whiteboard. What if you don't want to use potassium permanganate? Well, then let's use osmium tetroxide. Now, osmium tetroxide is a wonderful molecule. I used it in graduate school, but you have to be careful with osmium because, well, one of the byproducts is it can coat your eyeballs. So I would rather use potassium permanganate and control the temperature. But if you really need it to stop at just the diol, osmium tetroxide does the trick. And no surprise, guess what osmium tetroxide looks like? Looks very similar. Okay, so it's going to come and sit on top, which is going to make syn addition. Now this one cannot be done in one step though. You have to go on. So this would be the first step. And the second step would be taking it off with sodium bisulfite in water. So your second step is going to cleave, bleep, bleep, and put hydrogens in its place. But the beauty is it won't go further. The only problem, or not problem, the only product you're going to get is the diol. All right, so that's two ways to make a syn diol. Okay, syn meaning they're on the same side. Well, if I ever show you a way to make a syndiol, I better show you a way to make an antidiol. So we can't violate stability or steric, so we're going to have to go about it in just a different pathway. So if we, I guess I should put up here antidiol. If you want to make an antidiol, we're going to have to go through a different pathway. And so I'm going to use, see if you recognize this. I'm going to use a peroxy acid to create an epoxide. Okay, so my first step is to make this wonderful epoxide, and remember, they're flat, so you can get the top one or the bottom one. Now that I have that, now I can open it up, because remember, this is highly strained because it's a three-membered ring. But now that I have that open, I'm going to open it, and I have that on this reference sheet somewhere. Hold on, let me find it for you. It's a little section for epoxides. Where are you? Okay, it is on the alcohol page all the way at the bottom. I'll pull that up in just a second. But now I'm starting with an entirely different functional group called an epoxide. And the way that you can open this, and remember, I'm trying to make a diol, so I'm just going to throw some water at it. And I could use water with an acid, or I could just throw water at it, or I guess I could just throw sodium hydroxide at it. In this case, it's going to end up with the same thing. So here's my little water. And oh, look, I can attack here or here. Now, normally there's a choice, but this is an OH, so I'm going to put an OH on both sides, so it doesn't matter which one I show. So I'm going to just attack there. Oh, look. That's going to pop off as an O minus. We hate O minuses popping off, but the reason this can happen is because that's an epoxide, that's a three-membered ring, and it's highly strained. Hence the reason you can do these different options. So wouldn't it be nice if I put the proton on first? Okay, the way I showed it, I would put the proton on second. So I can either rip that proton from right here, or there could be a separate acid. But in the end, I am ending up with an anti-diol. All right, so let's look at the conditions. We could use an acid and water, okay? That would protonate first. So I don't have to do it when I'm done. Okay, I'd still have to deprotonate the OH2, but if you add acid, you protonate first, and then you don't have to protonate it when you're second. If you just use water, you would have to protonate as a second step. And if you used hydroxide, probably the least useful way, if you used a hydroxide, then you would also have to protonate at the end. And boy, why do I always run out of room? Because I write too big, that's why. So if you used a hydroxide, you'd have to protonate at the end. But any of those variations are going to give you an antidiol. So I gave you two ways to make a syndiol, and there's one way to make an antidiol. And the way to do that is your first step is creating an epoxide. All right, back to the notes. All right, so we use potassium permanganate, we use osmium tetroxide to make syndiols. Beware of potassium permanganate because it can get a little out of control. So you're going to control it with temperature. So if you want to stop at the diol, use cold temperatures. And then I gave you a way to make a but you first have to go through an epoxide. All right, now let's see what happens if it gets a little bit out of control. Okay, this is called oxidative cleavage. Oxidative cleavage literally breaks or cleaves through a bond. So if we use potassium permanganate, it's going to cleave and it's going to form two carboxylic acids. So let's use that alkene again. And we're going to add KMNO4 to it. And remember that was under basic conditions. Only this time, I'm going to allow it to have heat. Now, in some reactions, room temperature is enough, but others you have to heat it up, okay? But there is some form of heat. It's not cold. All right, so my first step is this. Okay, so just like we did a moment ago, that's the first step. But the second step is if we have heat, we're going to cleave through that bond. Sorry, the easiest way for me to draw it is to draw it first and then erase it. Okay, so this, come on, this bond is gone. And I end up with that. But remember, this is an oxidizing agent, and I have a single OH. And I have a single OH. And in the oxidizing process, KMNO4 is very strong, and so it is not going to stop unless it has to. And so the next step would be, I don't like that lime green. There. The next step is going to be put a double bond on it. So that one would turn into this, and this one would turn into, it's easier to draw the two carbons. Okay, with the oxidative cleavage, you're going to end up with, in this case, it's a ketone. In this case, it's an aldehyde. So this one can't go on. So you're stuck with that one. But this has a hydrogen to give. And remember, that means there is a hydrogen directly connected to the carbonyl. So that one is going to go on to a carboxylic acid. So if you are using potassium permanganate, go to the whiteboard. If you are using potassium permanganate, you can either end up with ketones if it's inside, or you can end up with carboxylic acids. Okay, so the way to look at this is cleave and put the carbonyl in its place. But if you'll notice, that's an aldehyde, so it's going to continue on to this. All right, how about this one? Cleave, redraw the backbone without the double bond and put a carbonyl in its place. Oh, that one has to stop because it's two ketones. How about this one? Cleave, redraw the backbone, put double bonds in its place, carbonyls. Oh, these are both aldehydes, so they are going to continue on, and you would end up with two carboxylic acids. So for alkenes and potassium permanganate is strong, and it is going to continue on until it cannot oxidize anymore. So you will end up with ketones if it's, smushed inside, or carboxylic acids if you first go through an aldehyde. And you finish that step off, just with water and anything needed to protonate it. Okay, so the first step is the KMNO4, and then of course you would, if you will, finish it, quench it, whatever word you want to use, with water or acid. Oh, boy, I run out of room a lot. With acid or just water. Because in the end, you're going to have to protonate those carboxylic acids. All right, so that's one way of cleaving the double bond and putting carbonyls in its place. Well, my next question is, what if you don't want a carboxylic acid? What if you would wanted to stop at the aldehyde? Well, my answer to you would be don't use potassium permanganate. And so we're going to use something called ozone, and it's going to be called ozonolysis. Okay, so we're going to form an ozonide, okay? And it's going to yield either ketones or aldehydes. Okay, it will not continue on. It will not continue on. And so the conditions for this one is literally ozone, okay, like ozone as in the upper atmosphere. And then you're going to break that ozonide that we formed with, some aqueous zinc or maybe some acetic acid. Okay, but I have to break it. All right, favorite alkene. And then we're going to react it. Oh. Okay, that's not the right Lewis structure, but we're going to react that with ozone. And it's going to create first. And if you really need these exact mechanisms, by the way, I'm skipping steps. I'm just giving you the overall flavor. But if you'd like to see the exact mechanisms, either ask or, you can look them up. But it's going to make something like that. Okay, that's a terrible drawing, but that's called the ozonide. And this bond is cleaved to make, see if I can draw it. There's your ozonide. Okay, so it cleaved that internal bond, and if you will, shifted, and I made this nice, pretty ozonide. So that's your first step. If you want to get rid of that, that's where your second step comes into play, your zinc or your acetic acid. And it is going to turn into, okay, just like I did before, draw the backbone and then put a double bond in its place with an oxygen. But the difference is you get to stop. Okay, you don't have to keep going. So this aldehyde will stop. And so that is the power of ozonolysis, is it'll cleave the multiple bond, but it won't continue on to the oxidizing step. It won't continue on. Oh, how fun. Let me see if there's anything else. I'm going to go to the reference sheet so we can see that. All right. Different color, green. All right, so we just talked about this one. We made the epoxide and then we went on and opened it for an antidiol. The place that you see that, okay, I'll go a little slower so it doesn't make us sick here. is right here. We had an epoxide, and then we did a ring opening. Okay, it was just called hydrolysis because we used water, and that is how we made our anti-diol. That's what we used to make the anti-diol. Okay, back up. All right, the next one is I wanted to make a syn-diol. Remember, that means same side. A syn-diol, I gave you two different ways. So you can use potassium permanganate under basic conditions, but you have to control it with that cold. Or you could use the osmium tetroxide, and then it takes the second step to break it, and that will make your syn-diol. Okay, so there are three ways to make diols, one way to make anti, two ways to make syn. And then if you want to cleave through the ring, that is either ozonolysis, okay, it will stop at ketones and aldehydes, or you could use a warmer, okay, potassium permanganate, but you don't get to stop. It will continue on oxidizing until it cannot go any further into carboxylic acids. And that is the oxidation and the oxidative cleavage continuation for the alkenes. All right, until next time, jolly out.